All right. So I am back after a long hiatus. Um, yeah, but basically decided to start working on, I guess, coding problems again. So here I am, back at it again. Um, yeah. So I guess that's it. Basically, we're doing this problem called all tasks scheduling orders. I guess we'll start off by reading the problem. Let me actually add problem statement. Okay, so the problem statement is there are n tasks labeled from 0 to n minus 1. Each task can have some prerequisite tasks which need to be completed before it can be scheduled. Given the number of tasks and a list of prerequisite pairs, write a method to print all possible ordering of tasks meeting all prerequisites. So I have two examples here. Example one, we have three tasks, 0, 1, and 2, which is how it's defined here. Our prerequisites are in order for 2. In order for us to do 1, we have to complete 2 first, and then in order to do 0, we need to complete 1. So our only order is 2, 1, 0. Since 2 has no prerequisites, 1 has one prerequisite, and 0 has one prerequisite, but then it's also technically 2 because 1 has to be completed after 2, right? And then so here we have another one, 6 tasks. We have prerequisites here. I'm not going to read it out, but basically, um, by skimming through the results, we can see that we can have 0 or 1 go first. And after 0 goes, 1 has to go before we're able to get any other combinations. If 1 goes first, we can have 0 or 3, and then we can have um, a number of combinations afterward. So basically, what we're trying to do is accomplish this in, um, with our code, print all of these, uh, I guess, unique combinations. And so, with that being said, I'm going to start on the problem. So, with this problem, we're going to be using topological sort. Basically, because there is an order that we have to approach this in, right? We can't just grab, for example, 3 first. We have to, at least for this one, we have to do 0 or 1, and in this case, we have to do 2, right? So we have to lead with our topological sort implementation. So we have to import, if I can import correctly, we have to import deque here. And then so we're going to create a queue using deque. We're going to create, I'm going to call it prereqs. Basically, we're going to have I is equal to 0 because we know that it's always going to be 0 from 0 to n minus 1. So we can do I colon 0 for I in range of tasks, right? And then here we're gonna have this called completes. It's not necessarily completes because it's basic. I'm using completes. It might not be the best word here, but what I'm trying to say is when we complete this task I, we will be able to move on to another task. So basically, when we complete task I, we're slowly clearing out the prerequisites for any of the classes or tasks listed in this array. And so we can use this array to reduce this number in the prereqs map or dictionary. And then once that's 0, then that means we can perform that task or take that class, whatever you want to use. The reason why I have a space here is because if tasks is equal to 0, then we can just print nothing. We can print an empty array, or we can just print nothing. So you know what, we'll just do return. So we just won't print anything at all, right? And so here, this is the beginning of our topological sort. And then we're going to build the prerequisites and completes map. So for, I'm going to do A and B. You can do task A, task B, whatever you want. But for A and B in prerequisites, I'm just going to use the autofill. Prereqs of B, because like we said, this is task A and B, right? So B has one prerequisite, so 5 has a prerequisite of 2, right? So in order for us to do 5, 2 has to be completed first. So in this case, B, you'll do plus equals 1 because there is at least one task for B that has to be, that there's at least one task that has to be completed before we're able to do task B. So that's what that line is for. And then for completes A dot append, we're gonna append B. So basically, when we complete task A, we're able to go to task B and reduce one of the prerequisites because we already completed it, right? And once prerequisites of B or whatever task is equal to 0, then we're able to perform that task, or at least queue it up. We don't necessarily have to perform it right now. And so for I in range of tasks, because now we need to go through all the tasks to see what task we can perform first, because hopefully there is in some world where we are able to print or like perform a task, right? It is possible that we can't, but we should be able to here. So what we're going to do is if prereqs of I is equal to 0, which means we're able to perform this task. So we're going to do q.append I. So able to queue up that. And so now we have set up our basis. So all of this is the basis of topological sort, right? And so now we're going to perform our backtrack. And then I'm going to write in here fill with arguments that we need. So I'm just going to leave that empty for now because I need to define the backtrack method before we're able to fill out what we need, right? So we're going to define backtrack, and then we're going to leave that empty for now because we need to figure out what we need first, right? So if the length of our ordering is equal to the number of tasks, then we're able to print that's print order, print all orders. So I'm going to call that print all orders instead. And then so we're going to call this print order, right? And we're going to pass in ordering. And so here we're going to define print order, and we have ordering here, and we're just going to print ordering, right? So ordering is not defined, task is not defined, so we know we need an ordering and tasks. So tasks will just be taken straight from here, and then ordering is what our order is going to be. So we're going to have a DQ for that, right? Because we need, so since this is a backtracking problem, we're going to be able to need, actually, maybe we don't even need a DQ. Maybe we can just get away with a regular array. Because we just need to put things in and remove things out of it. So I think we should be able to just do that, actually. So if length of ordering is equal to task, then we just print, and we want to return because we don't want to perform any of the logic afterward. Or we could just do an else, but doesn't look as good, so we're going to leave it. So we're just going to do a return instead. And so here we're going to do for I in range of length of q, because we need to, if we're backtracking, we need to go through our queue, right? So we need to pass in our queue. I'm going to pass it in as the first argument of our method because arguably it's the most important. It's this queue that we've built up with all of the tasks that we are able to perform at this instant. And so for I in range of the length of q, which means whatever tasks we have when we call this backtrack method, we can perform those tasks in any order, which allows us to build this ordering, or whatever you want to call it, right? So here we're going to do a popped is equal to q I, and then we're going to do q dot remove I. Oh, popped actually. So the reason why I'm able to use removed is because since this is from 0 to n minus 1, we are guaranteed that all of these tasks have a unique identifier. And so we will always remove, and then since remove removes the first instance of the value that we're trying to remove, this will be fine. Worst comes to worst, you can always do like this q splicing, which is like from this to I plus q, whoops, plus q I plus 1 to the end. If I'm not mistaken, this does the same thing, but in this case, I'm going to do this because actually, I'm gonna leave that there just so we can see if it does work at the end. So we need to remove the first instance of it because when we call backtrack essentially recursively, we do not want to work on this task again, right? So now we're going to do ordering the append popped. We need to add this to the ordering because we are taking this task from the queue. We're taking it and we're going to, be doing it in this order. Now, what we need to do is for task in completes popped. So now we know we also need completes, right? But I'm gonna drop that here, and then we're going to put this here. So basically, completes tells us when we finish a task what tasks we remove prerequisites for because we're eliminating that prerequisite, right? So what we're going to do now is prereqs for the task minus equals 1. If prereqs for the task is equal to 0, then we're able to do q.append task, right? So now this also tells me that I also need prereqs. So prereqs, because I haven't passed it in yet, and then so prereqs. So we're going to pass in prereqs just so we're able to check it against what we have completed. The ordering here doesn't necessarily matter. You can do whatever order. For me, I sort of do it in the order of importance, or at least an importance that I see in it. So basically, we definitely need the queue because we need to go through it in order to recursively like backtrack and then make our ordering. Our ordering is also very important because it's a solution. I guess you can technically argue that it should go first. Close enough. And these are what we just used to help us complete the task. So these prereqs and completes, we built this so that we can perform the topological sort. And tasks is just for us to check whether or not we have hit the length, and then we're able to move on. Realistically speaking, maybe this can even be a global variable, but that's fine. And if you were to define this within print all orders, that might be able to work too. But working with other languages, I think I'm just a bit used to defining them each individually like this. Anyways, so once you have appended all of the tasks to the queue, we're able to call our backtrack method once again. So we're going to need the queue, the ordering, the prereqs, completes, and tasks. And so once we keep going back recursively, once we come back out of this backtrack, we need to potentially go to the next order, right? So coming back up to the example, when we first hit backtrack on example 2, we're gonna have both the 0 and 1, right? So our first iteration through popped will be equal to 0, and we're gonna go through and then backtrack and go all the way down to print all the orderings possible for 0, right? But now we need to address 1. So what we need to do is basically revert the queue back to the state before we did any of this, right? So now any of this actually. So now we sort of need to go backward, right? So what I'm going to do is q dot insert I popped, because we want to insert it back at the same index that we had before ordering.pop, because we added popped to the end of ordering, so we want to remove that now. And then for task in prereqs popped, if prereqs no, it's, sorry, wrong one. So we need to go to completes, right? Because it's for, yeah, we need to reverse this. So we need to go back to completes popped, and then we need to do this backward, because we need to check if it's 0 first, right? Or I guess you can just add 1 and then see if it's 1, but we'll just do it the safer way, essentially, where prereqs task is, if it's equal to 0, then we want to do q.remove task, right? So it's the same idea, where since all of these tasks are uniquely labeled, we're able to just call remove task, and it'll remove the exact the exact instance of it within the queue. And then regardless if it's 0 or not, we need to do prereqs for the task plus equals 1 to revert this minus equals 1, right? And so now that we're done with that, I think we should be good to go. Fill arguments with what we need. We have our arguments. I think this is actually good. So if we were to, I'm not sure if that was showing properly. Start debugging, run without debugging. That's not what I want. Run Python file in terminal. Do I not have Python? Interesting. Okay, let me see. I should have Python. So you start debugging, run without debugging. Am I even calling it? Oh wait, it's because I'm not calling it at all. That's why, haha. Funny. Didn't set up the thing properly. So we have 210. Okay, let's scroll back up. So we have 210, which is what we expect. And man, maybe it would have helped if I had whatever, it's fine. So what we'll do is, so we know this one works fine, right? 210. But for this is a bit longer, so what I'll do is mark these. So 014325, 014325. I'll mark it with the X, meaning that we got it. 013425, 013425, 013245, 013245, 013254, 013254, 103425, 103425, 103245, 103245, 103254, 103254, 104325, 104325, 130245, 130245, 130254, 130254. Wait, 130245, 130245, 130254, 130254. Okay, and 3 more. Okay, that makes sense. 130425, 130425, 132054, 132054, 132045, 132045. Yeah, so basically there we go. And I guess just for parity's sake, I'll cross this one out as well. Yeah, so basically this shows that you know, this is working, and we're able to, solve this problem. Any questions, comments, concerns, please leave it in the comments below, and guess I'll catch you guys next time. See ya.